Good morning and welcome to this third lecture under this module on adaptive signal processing. We are going to look at Wiener filters in this lecture. So let's try to understand what these Wiener filters do, and this kind of is the first uh, step we are taking, moving away from deterministic systems and getting towards time varying system, but we will not yet look at the time varying system part. So let's relook at the scenario we had considered earlier. So we have our, let's say, the signal which is of interest denoted as d of n, that goes into a system. Before going into the system, there could be some possible uh, corruption or change, as we had seen in the past lecture. So this corrupted signal is what we are actually observing. So x of n is the observed signal, and from this observed signal we want to actually find what d of n is, or estimate d of n, right? So how do we do that? We take this signal x of n, send it, let's say, through a system or a filter which we are interested in designing, so that this filter, when it operates on this input signal x of n, will give us an estimate of the original uh, signal d of n, and this hopefully is an uncorrupted version of the signal. Okay. How do we obtain w of n? What is this w of n? So this is the question we are going to answer in this lecture. So just to kind of relate to what typically we have done in deterministic signals and systems, this can be related to a filter design problem. So in a filter design problem, you have an input signal which could have many frequencies, say for example, from low frequency to high frequency components, and you are usually interested in designing a low pass or a high pass or a band pass kind of filter, so that this filter will filter out certain components, right? So relate to maybe a classical filter design problem. So of course the inputs there were deterministic signals. So we didn't worry about any statistics, and there was always a desired filters frequency response, right? Meaning it could be a low pass filter, or it could be a high pass filter, or a band pass filter, where we know the cutoffs and other defined definitions which characterize this frequency response of the filter which we are interested in. So once we know that, let's say this desired h of ej omega, let's say that h desired of ej omega, right? So this is the objective, to obtain h desired ej omega, and this, where there are many techniques to obtain this desired, and eventually once we have an estimate, we wanted to see that our estimated, let's say, desired filter, this difference will be closed, right? The difference between the actual filter which is expected, the designed filter is what we have here, which is an estimate. The difference between these two has to be small in some sense, right? So this was our objective in this filter design problem, and we had many ways of designing this filter. So as opposed to this, now we will move to a slightly different notion and see what is that we can do, right? So let's move on. So again the question is, how do we obtain Wn, right. So let's for a moment not worry about the d of n as we saw it, but we'll just look at starting from x of n what we would like to do, right. So we have our x of n going into this system. Say that system is W of n to indicate that this could be time varying. The output is d hat of n. Right? So to design this filter, what we want to look at is we want to take this d of n and compare this d hat of n with, assume that we have access to this original d of n, which in practice we may not have, but assume we have this d of n. So what we want to do is we want to use this d of n and compare it with our estimate d hat of n, and what would this give? This would give us an error signal, error in terms of how much is the desired signal or the estimate of the desired signal. I'll just write it here for better clarity. This is d hat of n. Right? How much is the estimate of the desired signal deviate from the original signal, which is what this error signal is, right. So using this error signal, what do we want to do? We want to minimize this error, right. Minimize this error E of n, right. So that if we minimize this error, then this W of n will give us something which is what we expect to do, right. Find W of n to minimize this error. Right? So once we have this some notion of doing this, representing this and trying to obtain W of n, we are probably in the right direction. To make it more specific, if we just look at the error, as we could see, these signals could be positive or negative, and same could be the case with our desired signal. So this error could also be positive or negative. So just looking at this error at a given instant and saying, okay, minimize this error at a given instant is not a good measure of the performance of a such system or what we want to expect. So instead of looking at this E of n, which is, let's say, minimizing this error E of n, where this E of n is, let's say, our d of n minus d hat of n, what we look at is, instead look at the mean square error. Of course, we could work back from and get this definition. So we said E itself is not a good measure. So one possible measure is just look at the absolute value, or maybe square it, so that way at least if it is a small value, you know that it is small. But then just square is not sufficient, because that's just giving a value at one instant. So we need to look at it over certain time samples or over time. So that essentially is why we want to look at mean of the square of this error, right. So let's define this error as such. So let's say this error function is, let's say, denoted as zeta, and we are looking at mean square error. So we are looking at the expectation, because we are looking at the square error, and so this is what we want to minimize, right. So this can also be just written explicitly as, what is this E of n? E of n is just the difference between the desired signal and an estimate of the desired signal. So this is the error function we want, and we want to minimize this error function zeta instead of trying to just minimize E of n, right. So now, so the problem reduces to find W of n to minimize this zeta. So if we can do this, then we have achieved what we want to do. But before finding this W of n, we will assume some things about this W of n, right. So one of the assumption is, we will assume this W of, let's say, just I will say, to be, yeah. So instead of assuming, instead of using a generic W, we will assume this W of I to be a finite length filter or system. So in some sense, it's FIR filter. So this is not a big restriction. This is just for us to relate directly to what we have seen in our discrete time deterministic systems and signals, and moving on to somewhat simpler so-called adaptive and optimal filter. So this is just a restriction which we will just use for now. If possible later at some point in time, I will say how this thing can be relaxed and how we could achieve more, right. So if we do assume such a filter, then we can write W of n or W of z, let's say W of z, just to say that is in z transform I want to write. So I can write, if it is a length p filter, I will say this is length p minus 1 W of L z minus 1, i.e. The coefficients of W0, W1 up to WP minus 1. Right? So these are the P coefficients of the filter which we are interested in. Right? So if we have this filter, then since this is just an FIR filter, we could write our desired signal or estimate of the desired signal as d hat of n, which is just a convolution of our, let's say, if you want to write, just say W of n convolved with our x of n, which can be written as just a convolution operation. So right now what we have done, we just assume the system to be FIR, and because we assume the system to be FIR, our estimate of the desired signal at d of n is just this, right. So now we could write this d hat of n as part of the error function, and we look at what happens to the error function, right. So what do we need to do? Having done this, now we want to find, again I will just rewrite what we want to do. Find W of, let's say, k, that's for all, find W of k 0 to p minus 1 to minimize zeta, right? This is what we want, and where so just to relate, where the zeta, as we saw before, is essentially expected value this d of n minus d hat of n. So this d hat of n is what we are trying to have here as the d hat of n, and so we'll see how to do this thing, right. So this now is essentially, just think of this as a function, and as long as this function has some nice properties, which it does because of its quadratic in nature, that we could try to differentiate or find the gradient of this function with respect to W and see where this value becomes minimum, right. So we need to find Wk such that the gradient of this or the differential of this with respect to this weight coefficient. Let's just for convenience make this conjugate this function. this to be 0. Okay. So, this is just saying this is making more generalized, so that the weights also could be real or complex, and if it is complex we will have to look at the conjugate case. The reason we want to look at the conjugate also is because the zeta is actually a function of E and E conjugate, which we can write like this. So, essentially dou by dou W star of K. This is for each coefficient. Zeta is this expectation. Mod squared E, we write it as E of n times this E of n conjugate. Okay. So, this is what we want to find. To do this, we will now substitute for E of n in this expression. So, this, as you see, this is a function of both, assuming again error also could be complex. So, if you expand it as a product of the non-conjugate part and the conjugate part, you can see this E conjugate will have it will be a function of this weight, complex weights, and which could have a conjugate term. Hence, we could either find the gradient with respect to the conjugate part or the real part, but to keep this gradient or derivative simpler, we are looking at the gradient with respect to the conjugate part, right. So, if you do substitute for this conjugate and use this linearity of the expectation, so we could write it this as E of n, and only since this is the conjugate, the real part will become conjugate gradient with respect to the of the real part will become 0. So, we will have this W star k times this E star n. Okay. So, this is equal to 0, which essentially if you now substitute for E conjugate, this we will have is expected value of E of n and dou by dou W star k times E of n is essentially d conjugate of n minus, we have a d hat of n, which is a convolution of L0 to p minus 1 W L times x n minus L. Right. So, this is what we have in terms of that is equal to 0, right. So, now we want to look at what is this conjugate term, right. So, what is this conjugate term? That is, note that dou E conjugate of n by dou W star of k, which is the term here. So, this is not a function of W, so this will go to 0, only this term here is a function of W, and that will be non-zero only when k is the index. So, accordingly we will have this to be x conjugate n minus k, right. So, that is this term. So, which if you substitute here, we will have this expected value of E of n times this minus x star of n minus k is 0. Okay. So, this is kind of just says that the error, which is the error out of the system which we are planning or designing, is if you look at this as an expectation and if these are two random variables, these are saying that these are orthogonal, right. So, which is essentially saying that that this input signal and the error signal, we will have a weight which is 0 when these things behave in some sense in an orthogonal way, right. So, this is a notion which again can be used later when we visit let us say adaptive filters, but for now what we want to see is we want to use this condition and now substitute back for this error E of n, so that we could write this and expand this in a form such that we could relate the weights to the input signal, right. So, one aspect which kind of I did not mention earlier, which is kind of implicit here, is we are looking at this expectation and note that these are all random processes, right. X is a random process which is input because it has some noise. Because of that, the error which is also dependent on this input signal is also a random process, right. So, there is some statistical properties which we want to use, and that is what will come up next. So, we will carry over from this equation and just rewrite it. So, which is essentially this expected value of E of n times this x conjugate of n minus k, that is equal to 0 is what we want. So, we will substitute for this E of n. E of n is essentially our d of n minus, it is like W transpose, but let me just expand it and write it as the convolution which we had written before. This is going to be W of L x of n minus L times our x n minus k, right. So, this is for k 0 to p minus. This happens for every, right. So, just let us keep that in mind. So, now we can bring in the expectations inside and separate these terms. So, we will have one term which is this expectation of d of n times our x of n minus k, minus the other term, again we can take the expectation inside. So, we will have summation L 0 to p minus 1 W of L expectation of x of n minus L. I am just writing it so that times x conjugate n minus k, right. This thing is 0. So, recall that these processes assume. So, for now, just to keep the solution simple, if we assume the input signal to be White's-end stationary, then what we obtain is what is called as the optimal solution for this problem. Okay. So, with that assumption on White's-end stationarity, what we could write is this term here will just be denoted as the cross correlation between d and x. So, we will denote this as r dx of k minus this is essentially L0 p minus 1. This again xn minus L times xn minus k. This is this cross or autocorrelation of the input process. So, we will denote that as r x x of k minus L. This is just subtract this indices by this. So, then that is what we have here. So, this is equal to 0 is what we have, or we could rewrite it and say that L 0 to p minus 1 WL or xx k minus L is equal to r dx k for 0 to p minus 1. Okay. So, minus, okay. So, this is what we have, that it is r dx of k. Right. Another way to write this is as we had seen in the past. So, this x's, if we denote this x's as vectors, and correspondingly if you look at the autocorrelation matrix, we can rewrite this summation for all p values in this form, which is kind of an useful way to write and denote. So, we will denote this Rx 0, right, when k is k and L are 0. Then similarly, you will have this Rx k minus L is 1. So, you will denote this Rx of 1, Rx of p minus 1 when L when k is p minus 1 and L is 0. Right? In this row L is 0. So, correspondingly, we will have W of 0, and that is the first k0 to p minus 1 for L0. Then you can do the same thing for L1. Then you'll have this correspondingly Rx1, Rx0, and so on up to Similarly, you can fill this up and we'll end up having Rx p minus 1. Similarly here, 0, and on the right we'll have W p minus 1, and that is equal to Rdx 0 up to Rdx. Sorry, this, yeah, Rdx 0 to Rdx p minus 1. So this is an useful notation to have. So this one term here is, I'll probably write again. This is Rx, this is our W, which is a vector, and this is R dx. So this notation here is useful, and we will revisit this. So let me write in the next stage what we have done so far. So accordingly, we have Rx, which is a matrix, times this W, which is a vector, is vector of dx. So this and from this, which implies this W is Rx inverse R dx. This W is the optimal filter if X of n is a wide sense stationary versus wide sense stationary. So essentially, to address the problem of, let's say in this case we were saying that the desired signal D is corrupted by some V, and then we wanted to, let's say, estimate which filter will help us remove that corruption of the original signal and get back an estimate of the D. So in that case, this W is the optimal filter if X of n is a wide sense proportional process, and we minimize the mean square error. So for that error function and FIR, and if we assume that it's a wide sense process and we want to minimize the mean square error, assuming that FIR has finite length or the W has a finite length, then this is an estimate that autocorrelation matrix inverse times the cross correlation. So note that from our discussion on random process, this autocorrelation matrix for a wide sense stationary process will be invertible because it's going to be a positive definite matrix. So we could, once you have these statistics, which is the key, if we have these statistics, then you could obtain this optimal filter W. Okay. So that kind of what is referred, this filter is referred to as the Wiener-Hopf or Wiener filter, FIR filter. So there is an IR version which I am not presenting here yet, but this is the Wiener filter, and the set of equations which we saw earlier, which are these equations involving the autocorrelation and cross correlation, these are also called as this Wiener-Hopf equation. So, I mean that just as a terminology, it's worth remembering and knowing. This set of equations come very often in statistical signal processing and modeling of systems. Hence, this is a very generic equation used in many places, but it comes in helpful and handy for us to arrive at this optimal filter, where we want to minimize the mean square error with a finite range filter. This can be looked at as the solution. Okay. So this W is our filter, and what this filter does is it essentially minimizes the mean square error. So I am not going to derive it, but I will let you derive this representation, that what is the minimum mean square error possible with this filter. So this is something which you should be able to understand, because the error, as we said, is minimized for this W. So which means we can also denote this W as the optimal weight. Okay. So once you know that this is the point at which the error is minimized, you should be able to use the minimum error function which we defined earlier, plug in for this W optimal, and you should be able to have a relation between zeta and the filter weights. And what you will see is show, okay, this is a task for you to show that the zeta min is essentially RD of 0, which is the, let us say, desired signal energy, minus RDX Hermitian times Rx inverse times RDX. So essentially this is saying that RDX is something which you can obtain, R inverse RDX is our optimal weight. So using this you should be able to say that this is the zeta min. So with that we kind of conclude this session on Wiener filtering, where we started off with objective to design a filter W, which will help us make an estimate of the desired signal D. And if we use this error between the desired signal and the estimated desired signal and minimize the mean square error of that error, we end up with this filter which we refer as this Wiener filter. And this filter is the optimal filter when we want to design such systems where we can statistically describe what is the input, and if the statistical nature of the input is such that it is a Whitesian stationary signal, and in this case the system was not time varying. So given that we can obtain a filter at some W, so time instant as W. Right? So next what we will move on is we will try to kind of move on to the next stage as to what if we don't want to do just W directly. We want to have some other way of iteratively finding W. Why do we need it is something which we will look at in the next module, after a motivation as to what this filter can do and maybe some examples on this filter, and then we will get started with the next lecture. So thanks for listening, and till the next lecture.